Hello, good morning to everyone. Today I will give a lecture on reference electrodes from the engineering chemistry syllabus, uh, module 1. This syllabus is prescribed by Vishwesvaraya Technological University, Belgaum. Before going to the reference electrode, uh, we must understand what is electrochemistry and how these electrochemical processes occur, what is the function of an electrode, etc. So to understand this electrochemistry, we must look at the definition of the electrochemistry, that is, which is a branch of chemistry dealing with the study of transformation of chemical energy into electrical energy and vice versa. That means this science explains how can we derive electricity out of a chemical reaction, and how can the electricity be applied to bring about a chemical change, or electricity can be applied to get a chemical reaction, a beneficial chemical reactions. That is electrochemistry. So both way we can do change of chemical energy into electrical energy and electrical energy into chemical energy. So to do this process, we need some cells which are known as the electrochemical cells. An electrochemical cell is a device which is used to convert chemical energy into electrical energy and vice versa. Now let us see that what is these electrochemical cells and how many types of electrochemical cells are available. First kind of electrochemical cells are galvanic cells or voltaic cells. It can be called as so these are the electrochemical cells which converts chemical energy into electrical energy. So out of the chemical reaction, we can derive the electricity. And examples are plenty. Example of a Daniell cell, example of a galvanic cell is a Daniell cell or a dry cell. And you can also note that here when we talk about the cells, cells are also known as the battery. Batteries and cells are same, and the batteries are working on this principle of the galvanic cells. So here in this module, the galvanic cells are very important to understand the function of a galvanic cell, construction of a galvanic cell are important to understand this entire module. And second kind of electrochemical cells are the electrolytic cells. In this kind of cells, we convert the electrical energy into chemical energy. That means electricity is applied to bring about any kind of chemical change. For example, and most widely used electrolytic cells does the electrolysis. Okay, so electrolysis of the molten salts. Sometimes when we derive pure metal from the metallic ores, we use the electrolytic baths. So electrolysis of molten sodium chloride can be done, or any kind of secondary batteries or reversible batteries. We recharge those batteries by the electrolytic method, okay, or electrolysis process. Now, let us say, since I have told that galvanic cells are very important to understand this module, therefore, let us first discuss that what is a galvanic cell actually, and I will explain this function of a galvanic cell by taking the example of the Daniell cell. This is the most widely used galvanic cell, and to understand the function of the galvanic cell, always we start with the Daniell cell. Now, how this Daniell cell is constructed, you can see on the screen from this diagram that any galvanic cell uh, is made up of two half cells. You can see one half cell, this blue colored half cell, or you can say that which the half cell which is on your left hand side. Here we have taken a pure zinc rod, and which is dipped inside the electrolytic solution. This electrolytic solution is made up of a zinc salt. Okay, so when you are taking a metal at this left hand side half cell, you must see that the salt must contain that metal. For example, here we have taken the zinc electrode, the salt we have taken, which is a zinc sulfate. You can take zinc chloride, you can take zinc nitrate. So make a solution of it and you get the electrolyte, and the zinc rod is dipped in that uh, electrolyte which contains its own ions. And similarly, at the right hand side, you can say here this is the pure metal is made up of copper, and this copper is again dipped in the solution of its own salt, that is the copper sulfate. You can take copper nitrate, copper chloride. So this kind of electrolyte are must. So what we understand is, whatever electrode you are taking, that electrode must be dipped in the solution of its own ions. Okay, and at the left hand side, this electrode or this half cell, we call it as anode, and this half cell we call it as cathode. Anode is the negative terminal of the cell, cathode is the positive terminal of cell, and both these electrolytes are joined through a U-shaped tube. You can see here this U-shaped tube is nothing but called as the salt bridge. This is a salt bridge. Why it is called a salt bridge? It is filled with a salt of potassium chloride or potassium nitrate. You can take, and this salt bridge actually helps these two half cells to remain neutral, that is, they prevent the polarization of the electrodes. Okay, and these two electrodes are joined through an external wire which is usually made up of copper, and these are externally joined through a metallic wire internally through a salt bridge. So this is overall this construction of a galvanic cell. And here I have taken the example of a Daniel cell. So I have taken, or in the Daniel cell, zinc electrode is taken as at the anode and copper electrode is taken at the cathode, and the anode is the negative, copper is the positive. You remember this. In galvanic cell, anode is the negative terminal and cathode is the positive terminal. So any kind of galvanic cell needs two different metals. It is according to the electrode potential of the metals. So a electrode potential, lower electrode potential, the metal which are having lower electrode potential is taken as the anode. Metal having higher electrode potential is taken as the cathode, and this is the basis of a Daniel cell or any galvanic cells. Now, if we talk about the functioning of the galvanic cell, that is, what is the function of the galvanic cell? It converts the chemical energy into electrical energy. So how it does so? We can see here that by taking the examples of uh, I will show you that what is the working of this kind of electrode. I will show you by writing the reactions. You will have to always, whenever you are explaining any galvanic cell, you must be able to explain that how it functions, that is how electrons are produced, how the electricity is developed, how we get the electricity from out of the chemical reactions. For this reason, you must explain it with the working principle with the reactions. So when we write the reactions, we must understand that two kinds of reactions are involved in this kind of galvanic cells. First one is the oxidation reaction. Oxidation means loss of electrons. Any reaction where the loss of electrons takes place is called as the oxidation reaction. Now, if you have a metal and if you represent the metal as M, for example, simple thing, metal, M for metal, okay? So any metal. So metal gets converted, or metal loses electrons, metal when loses electrons, it gets converted into a positively charged ions, electrons are liberated. Or you can write like this: metal is losing the electrons to get converted into metal ions. So in these two ways you can write the oxidation reactions, but I will here take or use this reaction, that is metal is getting converted into metal ions and electrons are liberated. Now for example, in the Daniell cell we have taken the metal as zinc and one metal as copper. Now if we compare, going to the electrochemical series, if we compare the standard reduction potentials of zinc and copper, we'll see that standard reduction potential of zinc is minus 0.76 volt and standard reduction potential of copper is plus 0.34 volt. Now let us understand what is standard reduction potential values, SRP values. Reduction potential, potential means the capability of the metal to undergo reduction. So you can see here this reduction potential, capability of the metal to undergo reduction. You can see if you compare these two values, you'll find that reduction potential of zinc is lower than the reduction potential of copper. That's why zinc undergoes oxidation very easily and copper undergoes reduction very easily. So these are the reasons why we take the two different metals for construction of a galvanic cell. So here, now we can say that zinc undergoes oxidation or the anodic reaction. How you write the anodic reactions? At anode, we have taken the zinc metal dipped in the solution of the zinc sulfate, and a zinc undergoes oxidation, means a zinc loses the electrons, and at cathode, you have the copper sulfate solutions, so which will gain the electrons or the which will undergo the reduction, that is copper ions will undergo the reduction, so it is the uh, copper. So copper ions undergo reduction to get converted into copper. So this is the loss of electrons is oxidation, we can say loss of electrons is the oxidation reaction, and gain of electron is the reduction reaction. And now in case of this kind of explanation of the Daniell cell, you must write what is net reaction occurring in the cell, net reaction occurring in the cell. You must here you must add these two equations. These two electrons are liberated and two electrons are accepted. Always remember, whenever you are writing this kind of reactions, you must see that how many number of electrons are liberated at anode, that many numbers of liberated are accepted at cathode. Okay, if not, you will have to multiply these equations and balance the reactions, just like algebraic equations. So here we can now write, add the two reactions, adding up the two reactions will get zinc plus copper ions are getting converted into zinc 2 plus and copper ions. You see here, I'm telling you in one shot because I want to explain the reference electrodes. That's why the basic things you should remember and you should understand. Here you see that oxidation of the zinc is taking place, and you can see the oxidation state or valence of zinc here is 0. It is increased to +2. So when the oxidation takes place, the valency of the metal increases here 0 to +2, right? And then you see these copper ions. Copper ions are accepting the electrons, getting reduced to the pure copper. Here you see, compare the valencies. You can see here this +2 is converted into 0. And that's why it is called as a reduction, simple. And any reactions, it is a net reaction, okay, net chemical reaction. In the net chemical reaction, you can see that both these oxidation and reduction reactions are taking place. So these combine, if you combine these two in a reaction where oxidation reduction takes place simultaneously, that reaction is known as the redox reaction. So redox reaction makes the basis or the fundamental of any galvanic cell. So due to this redox reaction, we can derive the electricity from the cell. And why we can derive this electricity from the cell, you can see here now it is clear. Whatever I have explained, that two electrons are liberated at cathode. Sorry, electrodes are liberated, two electrons are liberated at anode. They travel through the external circuit and they reaches to the cathode. They're accepted by the copper ions. Okay, so there is a flow of the electrons from anode to cathode. What is electricity? Why we can derive electricity? Electricity generation occurs due to the flow of electrons. So whenever you are explaining any kind of galvanic cell which can produce electricity, you must show that how there is the liberation of the electrons and the consumption of the electrons, how the flow, how these electrons flow from the anode to the cathode. And since at anode the electrons are liberated, therefore anode is the negative electrode and cathode is the positive electrode. So here the concentration of the electrons are more. So it is negative, it is positive. Always remember, I am discussing about the galvanic cell. In galvanic cell, anode is negative, cathode is positive. This is not the case for the electrolytic cell. Electrolytic cell, just the opposite thing occurs. So electrolytic cell is not my focus now. I am only focusing on the galvanic cell. I hope this is clear. And now we'll look at a very quickly, we'll look at some important definitions, what the student should remember for this module. That is the single electrode potential. What is the electrode potential? Electrode gets a potential. Why electrode gets a potential? Due to the creation of the charges on the electrode surface. So on any electrode surface, there is a creation of the two layers. One is a negative charges due to the production of the electrons. Another is due to the production of the metal ions. There is a layer of the positive charges, and due to the two kinds of charges are accumulating on the surface of the electrode, therefore all kinds of electrode gets a potential, and that potential is known as the single electrode potential. Now if we try to understand, we should understand, we can again take this example of the galvanic cell. Electrode potential, what is the electrode potential developed at the zinc electrode surface? What is the electrode potential developed at the copper electrode surface? Okay, so since you have taken two different metals, two different electrodes, the potential developed at the two different electrodes will be always different, and that is why in a galvanic cell we take the two different metals, because you will get the two different electrodes, and the difference in these electrodes will give you a difference in this electrode potentials, will give you this EMF of the cell, electromotive force of the cell, like what is the voltage of the cell generated by using the two electrodes, that is called the EMF of the cell. EMF of the cell, right? EMF, electromotive force. What is electromotive force? Electromotive force is the electrode potential at cathode minus electrode potential at anode. Okay. Okay. What is this difference? If EMF is 0, that means you do not have any voltage from the cell, from the galvanic cell. Now the unit of the EMF, unit of the electrode potential, all the units are in volts. You can see that if you are using any kind of battery, you can see that how much voltage it generates, it is written over the battery. For example, your cell phone battery, if you can open the battery, you can see what is the voltage it generates. You can note it down, or you can understand in that way. Any kind of battery can see how much voltage it generates. So this volts or EMF of a cell is nothing but the difference in the electrode potential of the cathode and the anode. And always remember that if a reaction is this redox reaction is spontaneous, that means the reaction is feasible, or due to the reaction you get the electricity generated. When the reaction is spontaneous, when the EMF of the cell is positive, always remember this. So always the EMF of the cell must be positive. In which case EMF of the cell is positive? When the electrode potential of cathode is greater than electrode potential of anode. Here you can see where what I have shown you. Electrode potential of cathode is greater than electrode potential of the anode. For example, if you want to calculate the EMF of the cell of a Daniell cell, you can calculate in this manner. E cell of the Daniell cell is equal to plus 0.34 minus 0.76 volt is equal to plus 1.10 volt. You can see Daniell cell, how much voltage it can create. One pair of electrode. Okay, here we have taken only one pair of electrode. One pair of electrode can generate a voltage of 1.10 volts, right? So if you want more voltage, you can arrange the electrodes in parallel or in series to generate more electrodes, more voltage, right? So again, I'll go to now to the next slides. That is the definitions. One single electrode potential means what? It is defined as the potential developed at the interface between the metal and the solution when a metal is dipped in a solution containing its own ions, and it is represented as E. Okay. Now we'll go to the standard reduction potential or standard electrode potential, which is denoted by E naught. So try to understand this difference. One is the general electrode potential, another is the standard electrode potential. And always remember these electrode potentials we always consider as the reduction potential, that is the potential during the reaction process. So it is defined as the potential developed at the interface between the metal and the solution when a metal is dipped in a solution containing its own ions at unit concentration. This is important. When the concentration of the electrolyte is 1 molar, that is unit concentration, right? Of unit concentration and at 298 Kelvin. These two things should be maintained. That is, the concentration of the electrolyte must be 1 molar and the temperature must be room temperature, that is 25 degrees centigrade or 298 Kelvin. If you are maintaining these two conditions strictly, and you are getting or calculating the reduction potential values, then it is called as the standard reduction potential, right? And always it is not like that you are taking the metallic electrodes. You may take some electrodes which are gaseous electrodes. Okay, I will discuss it later. Gaseous electrodes like standard hydrogen electrodes. So if you are using the gaseous electrodes, then you will have to consider the atmospheric pressure or the pressure, at what pressure you are maintaining the electrode. So instead of this consideration of the electrolyte, you must say that this pressure of the electrode is this much. That is unit pressure, 1 atmospheric pressure should be maintained and 298 Kelvin temperature is maintained. Then it is called as the standard electrode potential. And the electromotive force, that is the potential difference between the two electrodes of a galvanic cell, which causes the flow of current from an electrode with higher reduction potential to the electrode with the lower reduction potential, that is from cathode to the anode. It is denoted as E cell, and E cell is equal to E cathode minus E anode, right or left, or cathode and anode, right? So this is the formula for EMF of the cell. Electron flow from anode to cathode, current flows from cathode to anode. So now I will go to the main topic what I wanted to discuss today, that is the reference electrodes. And what are now the reference electrode? Now you understand what is electrode, what is electrode potential, standard electrode potential, and how these electrodes are important for construction of a galvanic cell, or construction of a battery for that matter, we can say. So now I will go to the reference electrodes. What are the reference electrodes? Reference, what we refer. Okay, so reference electrodes are also called as the standard electrodes. You should have a standard value in front of you to measure whatever experiment you are doing, whether that experimental result can be compared with the standard values or the reference values. So reference always means the standard values, right? So what are the reference electrodes? The electrodes of known potential are called as reference electrodes. Electrodes of the known potential. Now, whatever I have discussed during galvanic cell, how these electrodes are taken, I have never told you that what is the electrode potential of any electrodes, how can we measure it. Only the standard values are known, like the standard electrode potential of the zinc electrode is minus 0.76 volt. Standard electrode potential of the copper is plus 0.34 volt, right? These are called the standard potentials. But if you are not maintaining any standard condition, how do you know that what is the electrode potential of that particular electrode? So if you do not know it, we call it as simply as the electrode. If you know the potential of the electrode, you call it as the reference electrode. So electrodes of known potential, that is very important. That which are the reference electrodes? Electrodes of the known potential are called the reference electrodes. The electrode potential of reference electrode is stable and reproducible. Using reference electrodes, the potentials of other electrodes can be measured. So this is the real application of the reference electrode. Why we need reference electrode? Why we need to understand the function of a reference electrode? Because by using the reference electrode, we can determine the potential of any other electrode. You take any metal, make it as an electrode. You can measure the potential of that electrode with the help of a reference electrode. Now, how many types of reference electrodes are there? There are two types of reference electrode. One is the primary, another is the secondary. So what are the primary reference electrode? Basically, primary reference electrode is standard hydrogen electrode. This is called as a primary reference electrode. Why it is called as primary reference electrode? Because the standard hydrogen electrode has the electrode potential as 0. Its electrode potential is 0. That's why this electrode is known as the primary reference electrode. So this standard hydrogen electrode potential is declared to be 0 at a temperature of 298 Kelvin. This is because it acts as a reference for comparison with any other electrode. So what is the reaction taking place at standard hydrogen electrode? Standard hydrogen electrode is made up of the construction part is like this, that is you need a inverted jar where there is a hole for or vent for the passing of the hydrogen gas, and this is a platinum electrode, and it is covered with the finely divided platinum black, and that's why it is called as platinized platinum electrode, and which is dipped in a solution which contains the 1 molar HCl solution. 1 molar H plus ion should be there here. That means what? This hydrogen gas is in contact with the H plus ions. This is the construction. This is how the standard hydrogen electrode is constructed. And when this electrode is maintained at 298 Kelvin and the hydrogen gas pressure is at 1 atmospheric pressure, then this is known as the standard hydrogen electrode and its electrode potential is 0. So what is the reaction taking place here? That is obviously when the hydrogen is oxidized, that means what? H plus ions, hydrogen gas is converted into H plus ions, and reduction of the hydrogen means hydrogen ions taking up electrons getting converted into hydrogen gas. So we can say that this hydrogen gas and the hydrogen ions are in equilibrium with each other at the surface of the hydrogen electrode or the standard hydrogen electrode, right? But what happens is this primary electrode has many demerits or disadvantages, because when we are talking about anything which deals with the hydrogen gas, always it is dangerous, because you'll have to maintain that hydrogen gas at 1 atmospheric pressure. You'll have to handle the hydrogen gas which is very highly inflammable. It is dangerous. So maintaining that hydrogen gas in a cylinder and then maintaining it at 1 atmospheric pressure is difficult. Okay, and then what happens is sometimes we won't get this pure hydrogen gas. It contains various kind of impurities, like maybe it is mixed with H2S gas or any kind of sulfur impurities. So these impurities may poison the platinum electrode. Poison the platinum electrode means they may deactivate the platinum electrode, which can alter its potential value. So when there is the poisoning of the electrodes, you are using this standard hydrogen electrode for measuring the electrode potential of any other electrode, then what happens? You may not get the accurate value or accurate result. You are measuring the, suppose you are measuring the electrode potential of a zinc electrode by using the standard hydrogen electrode, and you may not get the accurate value of the electrode potential of the standard hydrogen electrode. So these are the demerits of the hydrogen electrode. That means for all the cases we may not use the standard hydrogen electrode. Therefore, we have to seek for the alternate arrangements, and this is how there is the discovery of the secondary electrodes. And what are the secondary electrodes? Again, the secondary reference electrodes which are not having their standard electrode potential as 0. Okay, the value is not 0, but the value is constant. So secondary electrodes have the constant electrode potential and stable electrode potential values at a particular temperature. They are calibrated with respect to standard hydrogen electrode. Okay, and they have least potential gradient with temperature. The potential values are reliable and measurements can be made with great accuracy. So these secondary electrode potential values, you can say that they are stable and they are reproducible. They are very much reliable. They do not change with the change of temperature or pressure. They always show a constant value. So due to these advantages of the secondary electrodes, we use these secondary electrodes nowadays as the standard reference electrodes. So remember, I am discussing this now, the reference electrodes. I am now focusing on the secondary reference electrodes, and the most widely used secondary reference electrode is Calomel electrode. Remember, most widely used secondary reference electrode is a Calomel electrode, which is used in the chemistry, ordinary chemistry laboratories for various important purposes. So when we are doing this engineering chemistry laboratory practical sections, practical experiments we are handling, we are using the Calomel electrode. Now first let us see how a Calomel electrode can be constructed. Here you can see the diagram for Calomel electrode. This is consisting of a glass tube. You can see this glass tube. This is all made up of glass tube, and it has two openings. You can see here, this is a very small opening, and this opening is for filling the potassium chloride solution in this tube, and this is another opening, a side tube, which can be joined to any other electrode, okay, which acts as a salvage. And first of all, we'll have to pour some pure mercury at the bottom of this glass tube. You can see mercury is placed at the bottom of this glass tube, and above this mercury layer, we have to put another layer of calomel and mercury paste. Okay, so what is calomel? Okay, calomel. Calomel is nothing but mercurous chloride. Mercurous chloride, you can see mercurous chloride, Ag2Cl2. This is calomel. Mercurous chloride. This is a salt of mercury. Now you see here, this mercury is in contact with mercurous chloride. Mercurous chloride is in contact with, or the entire tube is filled with potassium chloride solution. So it is a metal salt iron electrode. So this can also be classified in this manner: metal salt and iron electrode, right? So this is the construction part of the Calomel electrode. Here you have another inner glass tube. Inner glass tube is fitted with a platinum wire, and this platinum wire should be dipped in the mercury layer for the external contact. So the entire construction of Calomel electrode is like this. Now remember, this is reference electrode. All the reference electrodes are a single electrode. With this single electrode, you cannot do anything. You have to join this electrode with any other electrode to make a complete cell. So complete cell means, like I have told in my lecture previously, that it is a Daniell cell is a complete cell. A complete cell needs two electrodes and the electrolyte. Two electrodes and the electrolyte. Okay. So any reference electrode, whether it is a standard hydrogen electrode, it is a Calomel electrode, or any other secondary reference electrode, it is a single. Either it is anode or it is cathode, right? So if it is anode, it needs a cathode to make a complete cell. If the reference electrode is a cathode, it needs an anode to make a complete cell. Clear? So this is the construction part of the Calomel electrode. Why we call it as Calomel electrode? Due to the presence of mercurous chloride, that you remember. So what I have told you, that is shown here. Calomel electrode is a metal sparingly soluble salt electrode. Sparingly soluble salt is the mercurous chloride. And how we represent this electrode? Any electrode can be represented. Always it is not possible to draw the diagram and explain the construction part. Sometimes uh, very quickly we do the things, we write or represent that electrode in a single line. So one line representation is this, that is, we write like this: mercury mercury is in contact with mercurous chloride. Mercury is in contact with mercurous chloride, which is in contact with KCl. So representation you can see from here. If I want to write the representation, see here, better I write here. Mercury at the bottom of the glass tube, then the single bar, and then the salt Ag2Cl2, which is in contact with the KCl. Okay. Now this single bar, this is the phase separation. Okay. This is the phase separation, like, or the phase boundary. You have the mercury, then you have mercury chloride, we have the solid phase. This is the liquid, this is the solid, this is again a liquid solution. So to explain this, like, to separate the phases, we use the single bar. Okay. So this is the representation. Now this representation you can do or write from the other side also. You can start from KCl, then you can take, it is in contact with the mercurous chloride, and then it is in contact with the mercury. So it depends on this, writing this representation depends on whether you are taking this electrode as the anode or the cathode. So if you are taking or considering taking this electrode as the anode, you must start with the metal. Okay, that is the rule. This is the IUPAC system. So if you are writing the electrode or using the electrode as anode, start from the metal, end with the solution. If you are using the electrode as the cathode, start with the solution, end with the metal. This is the rule. Okay. So in both ways, you can represent the Calomel electrode. Okay. Now, Calomel electrodes are of three types. Again, it depends on the concentration of the KCl. It can be normal Calomel electrode, decinormal Calomel electrode, or saturated Calomel electrode. Remember this again. You are taken KCl solution. So this KCl solution concentration, what is the concentration of the KCl solution? Whether the KCl solution is of 0.1 normal, or KCl solution is of 1 normal, or KCl solution is a saturated solution. What? So you will have to mention that also, right? If you know it, then better, or otherwise you'll have to get the data that which kind of Calomel electrode you are using for your experiment. So three kinds of Calomel electrodes are available. Now this working part, how this Calomel electrode works. As I have told you, the Calomel electrode can act as anode or as cathode since it is a single electrode. Therefore, the potential of the Calomel electrode depends upon the concentration of the chloride ions in the solution or the KCl solution. Now, if we start like how this electrode acts or liberates electrons if it is anode. Okay, so if the electrode is used as anode, then the half reaction, because it is a half cell or it is a single electrode, what will be the half reaction? It acts as anode. Which kind of reaction takes place at anode? At anode, always remember, oxidation reaction takes place, right? So oxidation reaction takes place. Oxidation of the metal. Metal is the mercury. So the mercury is oxidized to the mercurous ion. Okay, this is the mercurous ion. Why we call it as mercurous ion? Because this mercurous ion is a dimeric ion. Mercury bonding is there. It is a diatomic ion. So since it is 2 plus, we can say that each of the atom is having charge plus 1. Lower valency is denoted with like OUS, higher valency is denoted with IC. You know this, if your metal is mercury, you can have two ions, one is mercurous ion, another is mercuric ion. Mercurous means its valency must be 1. Mercuric means its valency must be plus 2. So plus 1 and plus 2. Here we have written here, it is, you are seeing that this is plus 2. Actually, it is not so. Since it is a diatomic ion. So if we divide it among these two atoms, it is the valence is plus 1, and that's why it is called as mercurous ion. So mercury is oxidized to mercurous ion, electrons are liberated, and this mercurous ion is in contact, it comes in contact with the chloride of this KCl, chloride of this KCl. So here Cl minus from KCl. Okay, so mercurous ion reacts with the chloride ion to form Hg2Cl2 mercurous chloride. So this is the anodic reaction. You can see overall reaction, anodic reaction is, you can see here the electrons are liberated after all these things. Mercury reacts with, net reaction is mercury reacts with chloride to produce Hg2Cl2 and 2 electrons are liberated. Okay. So if you add these two reactions, you can have Hg2 2 plus and Hg2 2 plus cancelled in both sides, and you have 2 Hg. Add these two equations, Hg 2Hg plus 2Cl minus is equal to Hg2Cl2 plus 2 electrons. That is the net reaction. If it acts as anode, remember that. Now, if the electrode acts as cathode, you are using this Calomel electrode, you have taken another electrode as the anode and Calomel electrode as the cathode. Now, if the Calomel electrode acts as cathode, then which kind of reaction will take place? The main reaction will be the reduction reaction. This is the reduction reaction. You see here, electrons are consumed by the mercurous ion. Okay. So mercurous ion comes from where? This decomposition of the mercurous chloride gives the mercurous ions. Mercurous ions, they accept the electrons to get deposited as the mercury. So overall reaction is mercurous chloride accept the electrons to get deposited as the mercury and the chloride ions. Okay. Clear? You see here. This reaction now, we say that mercurous or Calomel electrode acts as cathode. So cathode means acceptance of the electrons. Mercurous ion gets deposited as mercury. Okay, this is the reduction reaction take place. Now, if I take this reaction as the number 2, if I write, and the previous reaction is the number 1, here, if it is number 1, then you can compare these two reactions. See this equation number 1 or the reaction number 1 or the anodic reaction and the cathodic reaction. You will, if when you compare these two reactions, you'll find that they are reverse of each other. Okay. So in any kind of reference electrode, when you explain, you must explain in this fashion. If it is anodic, what is the reaction, how the electrons are liberated. If it acts as cathode, how the electrons are consumed, and then compare the two reactions, you'll find that they're reverse of each other, and we can say, we can write this reverse reaction, and that is the equilibrium reactions. Equilibrium between the salt and the mercury. Okay. So these equilibrium reactions or an equilibrium exists on every electrode surface, and you must be able to write that equilibrium. So whenever we talk about the electrochemical cells, especially of galvanic cells, you remember that on every electrode surface there is an equilibrium between the pure metal and the metal ions. Okay, here you see. If I write the general equilibrium, metal ions, metal ions, equilibrium with the pure metal. This equilibrium exists on every electrode surface. You can see that reduction reaction is written in the forward direction. Why? Because every electrode potential means a reduction potential according to IUPAC convention. Okay. So now, since we have got the equilibrium, the Nernst equation for Calomel electrode can be written like this: E is equal to E naught minus 0.0591 log of concentration of the chloride ions. That means it directly shows that the potential of the Calomel electrode given by E is directly proportional to the concentration of the chloride ions. That means when you are taking the concentration of the potassium chloride solution as 0.1 N, the electrode potential of the calomel electrode is 0.3335 volt. Okay. When the calomel electrode concentration is 1 N, the electrode potential of the calomel electrode is 0.2810 volt, and most widely used calomel electrode is the saturated calomel electrode. Saturated solution of potassium chloride, when used in the electrode, its electrode potential is 0.2422 volt. This voltage should be, you should remember this voltage since it is a most widely used calomel electrode. Now a saturated solution we can prepare where you can dissolve the potassium chloride solutions in a minimum amount of water. Water is the solvent here, minimum amount of water, and when some potassium chloride is remains undissolved in that solution, that is called as the saturated solution. Preparation of a saturated solution is easy as compared to the standard solutions like normal solution or decinormal solution, and therefore the most widely used calomel electrode uses the saturated potassium chloride solution, and its voltage is 0.2422 volt. So the point to be noted here is the calomel electrode is a secondary electrode, secondary reference electrode. Reference electrode means the electrodes whose potentials are constant or of known values, and here you can see the electrode potential of three types of calomel electrodes are given, which are not zero. Okay, since their potentials are not zero, therefore they are known as the secondary reference electrode. Calomel electrode is the secondary reference electrode. I think this is clear now that what is a reference electrode? How many types of reference electrode is there? Why the standard hydrogen electrode is called as the primary reference electrode? Why calomel electrode is a secondary reference electrode? What are the demerits of the primary reference electrode, and how this calomel electrode is advantageous? So advantages of calomel electrode is on that very easy for construction, as you can see, and there is no maintenance problem. You can keep it as you like at a room temperature in the laboratory, and it goes for a long time. Like when we purchase one calomel electrode, it goes for at least for 10 years. We can use without any disturbance, and its potential is reproducible and stable potential. Only disadvantage or demerit of the calomel electrode is that it uses mercury. Okay, earlier we are not aware of the toxicity of the heavy metals. Mercury is a heavy metal, it is toxic, it has plenty of health hazards. So it is like you are using a thermometer which uses mercury, and the thermometer gets broken and the mercury comes out, and if you comes in contact with that mercury, you may have some kind of health hazards, kind of many things, like it is like a poison. So we should be very very careful when we are using any kind of equipment which uses mercury. So in that way, the calomel electrode, little care should be taken that since it is made up of glass, it should not get broken. Okay, and the thing is that calomel electrode should not be used at above 50 degrees centigrade, because the mercurous chloride breaks down, yielding the unstable readings. So if you want your readings or measurements should be accurate, then you use it, better to use it at a temperature range of like room temperature or 30 to 35 degrees centigrade. It is okay, and should not operate at 50 degree or above 50 degrees centigrade. It may not give you the accurate results. So these are the disadvantages, but if we take care, if we handle it properly, this is very convenient secondary reference electrode. And the applications are most widely used application is the use of can be used in a pH meter. So another reference electrode is a glass electrode, and glass electrode, calomel electrode can be combined together, and this glass calomel electrode assembly can be used to measure the pH of any solution, any water sample or any solution. So most widely used application of calomel electrode is used in the pH meter and used to measure potential of any other electrode. So if you combine a calomel electrode with a zinc electrode, you can calculate the potential of a zinc electrode, you can calculate the potential of the copper electrode, iron electrode, any kind of electrode. You can measure the electrode potential by using the calomel electrode. So I hope this today's lesson is useful and you can understand by listening to this lecture. So for today it is over, and now I will go to the next topic.